Hola! We will start by deriving Newton's second law into its most common form, starting from the impulse-momentum theorem. Remember that the impulse-momentum theorem is a way of expressing Newton's first law. We will start by isolating the force. This form is actually how Newton wrote his second law in algebraic form. We should emphasize that this is the average net force acting on the particle through the elapsed time interval. Using that momentum is defined in equation form as mass times velocity we get. A point particle is defined as an object where size and shape does not matter. That indirectly implies that its mass remains unchangeable and the difference only applies to the velocity. The change in velocity over an elapsed time is the definition of the average acceleration. We now have Newton's second law in its most common form. If you like to take a minute to soak this little derivation up, you can pause the video. Next, we will summarize Newton's laws for a point particle. The first law is known as the law of inertia. Inertia is the resistance to a change in motion, and for the linear case, that is mass. Recall that Newton defined motion as momentum. The first law states that a particle in a state of motion will remain in the same state of motion unless a net non-zero force is acting on the particle. The second law quantifies the first law. The sum of all forces acting on the particle, cause, will change its motion, effect. Note, this is valid for a point particle. If we have a system or mass is changing, we must use a more general form of Newton's second law that we saw a minute ago. The third law is known as the law of action and reaction. For every particle experiencing an interaction due to a second particle, there is an equal and opposite interaction on the second particle. This implies that forces always appear in pairs, but never act on the same particle.